Hello everyone, welcome to another lecture of population modeling. In the previous class we discussed how to write down equations for two species competition models, and we also did a bit of analysis. We found the equilibrium points, and based on the relative strengths of interspecific and intraspecific competition, we also made some educated guesses about what are the possible outcomes, right. So, now today we will do one further analysis to mathematically more rigorous analysis to understand when does one species competitively exclude the other, when can they coexist. Okay. So, to do that, let us recall the equations which are Lotka-Volterra competition model equations. Okay. So, remember that the basic premise was that both the species follow a logistic population growth in the absence of other species. Okay. And the key point here is that due to competition between species 1 and 2, you have this additional term. Okay. You have the additional term which is written in red fonts. Okay. This basically says that the presence of species 2 effectively increases the competition, and therefore, the growth rate of per capita growth rate of species 1. So, presence of species 2 reduces the per capita growth rate of species 1, right. And alpha 2 1 basically sort of indicates the interspecific competition strength of species 2 on species 1. Okay. Now, let us also write down the equations for species 2. Okay. Again here too we sort of work under the premise that in the absence of species 1, species 2 would reach carrying capacity K2, and it follows the logistic population model. However, in presence of species 1, there is an effect of species 1 on 2, and okay, and so therefore, we have this additional term of alpha 1 2 n 1. Following the reference of Gotteli, a primer of ecology, I am going to use the terms alpha 2 1 is basically, I am going to replace this by alpha, I am going to replace this by beta. Okay. Okay. So, now let us just before we go forward with the analysis, let us make sure we understand the underlying assumptions. Of this model. Okay. As before, we have ignored many details of biological organisms and how they actually live, right. For example, we have ignored the fact that they are spread in space and there is stochasticity in birth and death, right. Okay. And stochastic factors are totally ignored, right. And we have ignored the fact that many organisms have life histories and various stages in life. Structure within a lifetime is something again we have ignored, right. So, these are the various factors we have ignored in populations, and we are assuming that of course the resources are limited, which is precisely why there is competition. And we are assuming that the density dependence is linear. Right, which is why we just had simple linear terms that influence the growth rates as a function of both the species, right. And we also assume that all the coefficients such as R1, R2, K1, K2, which are the carrying capacities, and alpha and beta, they are all constants, they do not change with time. Okay. These are some of the major assumptions we made. Typically whenever we write down, whenever we write an equation that represents biological reality, there are really large number of assumptions we make, and what is really crucial is to understand what are the key assumptions that we have made. We do not have to necessarily list every assumption we have made, that might be a really long and impossibly long list, but what is really important is to understand what are the crucial assumptions, and in this context of two species populations, I think these are some of the important assumptions that we have made that is worth mentioning here. Okay. So, let us move forward to understand competitive exclusion and coexistence. Okay. So, remember that in this system there were several equilibria, right, and competitive exclusion basically means that only one species is going to be present at equilibrium. So, basically those equilibrium correspond to either one of these two. Equilibrium 1 is where only species 1 is present and species 2 is absent. Another equilibrium is when species 1 is absent and species 2 is present in the population. Okay. Now, let us use a very simple idea. Okay. Let us consider whether species 1 can actually competitively exclude species 2. Okay. So, the question we set out to ask is, can species 1 exclude species 2, and if so, under what conditions? Okay. To understand this, let us consider the worst possible scenario for species 1. Let us start with worst possible scenario for and even in that worst possible scenario, if species 1 can exclude species 2, it is always going to competitively exclude species 2, right. So, that is the basic idea. So, what is the worst possible scenario for species 1? So, worst possible scenario is as follows. Basically the initial condition is such that the entire system is occupied basically by species 2. So, basically species 2 is at carrying capacity, whereas species 1 is close to 0, it is hardly present. In other words, species 2 is at its carrying capacity, species 1 is really tiny and small, but not 0, okay, because of course if it was totally 0, then what can happen. So, this is sort of analogous to the idea of stability analysis. We know that these two are the equilibrium. When we have an equilibrium, if I make a small perturbation from the equilibrium, if the system moves away from the equilibrium, we call that an unstable equilibrium. The system comes back to the equilibrium, we call that a stable equilibrium. So, here basically this scenario corresponds to asking, okay, this entire scenario, whatever I call the worst possible scenario, is same as asking, is the equilibrium 0 K2 stable? That is the basic question that we are asking, okay. And then starting with 0 K2, where only species 2 is present, can species 1 invade even in this worst possible scenario, okay. So, that is what we are going to now understand. To do this, let us now go back to the equations, the load curve Volterra equations, and then see what happens, okay. Now, for species 1 to invade species 2, which is at carrying capacity, which is at its carrying capacity, the growth rate of species 1 at this instant must be positive, must be greater than 0. If the growth rate of species 1 is negative, of course, there is no hope for invading species 2, right. So, that is the idea. So, we basically ask, now remember that the growth rate for species 1 is nothing but dn1 by dt. So, we just have to basically write down the expression for dn1 by dt and check when is it going to be positive, even under the condition that species 2 is at carrying capacity, right. So, we know that the expression for this is this n1 minus k1 minus alpha k2 by k1. So, now let us just spare a moment here. Why did I write alpha k2? Okay. First remember that I am using the notation, the influence of species 2 on 1 as alpha, that is the first point. The second point is that the species 2 is basically at its maximum capacity, which is its own carrying capacity K2. So, basically I have replaced alpha 2 1 n2 by alpha K2 in this expression here, okay. That is what I have done. Remember that n1 is really tiny and this part is this part of the equation is always positive, right. For the entire growth rate to be positive, we would need this expression, the numerator of this expression to be positive. In other words, growth rate of species 1 dn1 by dt is positive if n1 minus k1 minus alpha k2 is positive, okay. Let me write this again. If n1 minus, sorry, I think I made a mistake here. I have made a small mistake in the expression here, let me just please note down. So, this really I got the two terms swapped. So, this should really have been k1 minus n1, okay. I am going to fix that now, okay. So, if k1 minus n1 minus alpha times k2 is positive, okay. Okay. Now, remember that n1 is a really small number. So, let us now ask, under what condition can species 1 invade species 2 which is actually at its carrying capacity. In other words, N2 is K2 whereas N1 is small but just greater than 0. To do this, and this is of course possible only when the growth rate of species 1 which is given by dN1 by dt is greater than 0. Only when the growth rate of species 1 is greater than 0, even if species 2 was at its carrying capacity, we can expect that the species 1 will invade species 2 and potentially therefore also exclude species 2 from the its existence, right. So, now let us understand under what conditions this can happen. For this to happen, we need to understand when the growth rate dN1 by dt is greater than 0. Remember that the expressions for dN1 by dt is given by R1 N1 times K1 minus N1 minus alpha N2 divided by K2, right. Okay. Now, in this equation, if this has to be positive, let us now look at each of the term. Now, the R1 N1, R1 is the growth rate of population N1 when it is really in small size, therefore, R1 is positive, and R1 N1 we always expect this to be 0. Therefore, for the entire growth rate to be 0, this quantity, the numerator of this expression in the bracket has to be greater than 0. Therefore, the product will be then greater than 0, right. Now, also recall that N2 is close to K2 and N1 is basically small and negligible quantity. So, I can write down this numerator as follows: K1, I can ignore N1 because it is really close to 0, and then I can write K2, N2 is as K2. So, but this has to be now greater than 0. And under this condition, which basically also translates as K1 is greater than alpha K2, which we can also write as alpha is less than K1 by K2. So, this is the condition under which species 1 can invade species 2. Okay. Let us now understand this condition biologically. Okay. Let us do that, let us consider two possible cases. The case 1 is when carrying capacity of 1 is equal to carrying capacity of 2. So, in such a case, species 1 can invade species 2 at its carrying capacity when alpha is less than 1. Remember what is alpha? Alpha is basically the effect of interspecific competition of species 2 on species 1. It basically measures interspecific competition effect of species 2 on species 1, right. It also is a relative measure. If alpha is less than 1, it also means that relatively interspecific competition is stronger for species 1 than the intraspecific competition. Okay. So, but alpha less than 1 basically means that the interspecific competition is now less, or in other words, SP2 is not a strong competitor. So, when the species 2 is not a strong competitor, that is precisely when species 1 can invade species 2, right. So, this condition K1 is equal to K2 really helps us understand that, but remember that K1 need not be equal to K2. So, I gave that special condition to understand the issues better, but remember that K1 and K2 need not be same. So, in that case we actually have a more general condition, which is that k1 greater than alpha k2 is the most general condition, which basically means that okay, as long as the carrying capacity of the species 1 is really large, larger than alpha k2, okay, it does not matter how big alpha is, it does not matter how big k2 is, it does not matter how strong the competition from species 2 to species 1 is, as long as the carrying capacity of k1 is really large, species 1 can invade species 2. If its carrying capacity is sufficiently large. I say sufficiently large because it must be sufficiently large, so that this inequality k1 greater than alpha k2 is actually met. Okay. But let me make one remark at this stage. The fact that species 1 can invade species 2 does not mean that species 1 would exclude species 2. Okay. In fact, what we need is that if we now start only with species 1, okay, then species 2 should not be able to invade species 1. Okay. That is also a necessary condition. So, let me make this point clear. For species 1 to exclude, competitively exclude, when I say exclude, what I really mean is competitively exclude. To exclude species 2, we need two conditions. One, species 1 must be able to invade species 2 when species 2 is at its carrying capacity, which I am sort of writing using the shorthand of sp2 or k2. In addition, sp2 species 2 should not invade sp1. Okay. So, we have so far found the conditions for the first one, mathematical conditions for the first statement, but we have not yet found the mathematical condition for the second statement. Let us now try to do that. So, what this means is that consider the equilibrium where only species 1 is present at its carrying capacity. Which means that N1 is close to K1, whereas N2 is greater than but very close to 0. Okay. So, we are looking at this equilibrium. Okay. And now we need to ask what is the growth rate of species 2 now. Now, species 2 should not invade species 1, which means that we want to know when is this true. So, let us see when is this true. To do this, we need to write down the expression for the growth rate of species 2, which is dN2 by dt, starts with R2 N2. Remember that this part is always positive. Okay. So, we therefore have to look at the term in the bracket, which is K2 minus N2 minus beta N1 divided by K1 K2. Now, for this to be negative, we should have this numerator to be less than 0, and that is true if K2, and if these two, if this is positive and if the numerator is negative, then the entire term will be negative, which means that minus beta N1 must be negative. Remember that we are now looking at the case when N1 is close to its carrying capacity, N2 is close to 0. Putting these two conditions, what we find is that K2 minus beta K1 must be less than 0, which is same as saying K2 must be less than beta K1, which is also same as saying beta is greater than K2 by K1. So, both the conditions are very interesting again. So, let us understand both these ways of writing the same point is very interesting. What is beta greater than K2 by K1? Beta is the effect of species 1 on species 2. It means if the interspecific competition effect of species 1 on species 2, if it is greater than the ratio of the carrying capacities K2 to K1, then species 2 cannot invade species 1. Another way of saying it is if the carrying capacity of K2 is not sufficiently large. Okay. So, that is when again species 2 cannot invade species 1. Okay. So, basically put together what do we find? Species 1 competitively excludes species 2 if two conditions are met. The first condition is that, let us go back and note that what it is. It is that K1 is greater than alpha K2 . Secondly, K2 is less than beta K1. So, sort of what this is sort of intuitively trying to say in summary is that the interspecific competition effects of species 2 on 1 must be small, whereas the interspecific species competition effect of species 1 on 2 must be large. Okay. And this can happen directly via alpha and betas and indirectly via carrying capacities being large. Okay. And let me make one remark here. Okay. One might ask, what is the point of this complicated mathematical modeling involving lots of equations? Now, if you had asked me, when we wrote down the equations for two species competition models, right, I could have probably said that whether species 1 beats species 2 or vice versa would depend only on alpha and beta. Okay. It would have been difficult for me to guess that the carrying capacities also play a role, and in fact in the previous video where I made an intuitive sort of picture of how alpha and beta determine the outcome of competition. You might recall this graph where we had alpha and beta on two axes. Okay, alpha greater than 1 meant alpha equal to 1 and beta equal to 1 meant that the interspecific and intraspecific competitions for both species are equal, and depending on which part of this, we can now divide this plot into 4 different parts. One corner where the alpha and beta are both less than 1, meaning the intraspecific competition is dominant, right. This would be the block where intraspecific is more than interspecific, and this would be the opposite, right. This is the case when interspecific competition is stronger than intraspecific competition, and one can fill the other 2 blocks as well, right. Now, we made a sort of a intuitive expectation of what the outcomes are going to be, and it was a pretty reasonable expectation, but remember that in our intuitive expectation the K1 and K2 did not figure out at all. The role of carrying capacities of both the species did not figure out at all, and that is something that came only because we were able to mathematically rigorously analyze and find out the conditions when species 1 can invade species 2, species 2 can invade species 1 or vice versa. Okay. So, of course, that's really the power of mathematical modeling. It actually makes our predictions much more precise and helps us also test empirical predictions in a more accurate way. Okay. So far what I have shown you is the condition or rather set of conditions for species 1 to competitively exclude species 2. As an exercise, I encourage you to think about what are the conditions for species 2 to exclude species 1. Now, it should not be too hard to go back and do the same analysis, but just invert the conditions. For species 2 to exclude species 1, start with the condition which is worst possible scenario for species 2, okay, which would be that species 1 is in carrying capacity and species 2 is present in minuscule numbers, okay, and then see if the invasibility succeeds. To do that, you have to check if the growth rate of species 2 is positive even when species 2 is present in really small numbers and species 1 is close to its carrying capacity. Okay. So, and of course, that is insufficient. The second condition you will have to look for is if once the system is in an equilibrium of only species 2, can the species 1 invade or not? Okay. It should not be able to invade. That is when we can conclude that species 2 can completely exclude species 1. Clearly, you can also imagine coexistence, which is extremely important. Many species do coexist. So, what are the conditions for coexistence? So, let us just check that. So, again intuitively you can ask again when would coexistence happen? Coexistence can happen again, start with the worst possible scenario for species 1 and ask, can species 1 invade species 2 at its carrying capacity, and also ask in addition, can species 2 invade species 1 at its carrying capacity? If both of them are if the answer to both of them are in affirmative, that means we will have coexistence. And in fact, it should not be too hard to arrive at these two conditions. We already derived the condition for species 1 to invade species 2, right, and let us just go back to our notes and check what that was. Okay. For the species 1 to invade species 2, this was a necessary condition, K1 must be greater than alpha K2, right. For this one we know that, so the first condition is K1 must be greater than alpha K2, and remember that the same thing must happen, which is species 2 must be able to invade species 1 now, and for that we just have to look for the opposite of the conditions we derived here. In this case, when we were doing these calculations, we wanted the dn2 by dt to be negative. So, this was a condition when the system was in the equilibrium of only species 1, and we were looking at what happens if we introduce a small numbers of species 2, and we found that the growth rate is negative if K2 was less than beta K1. Now, if it was the opposite, meaning if K2 was greater than beta K1, the growth rate would have been positive, right, and and that means that both can now, if both these conditions are simultaneously present, that means that both can invade each other, and therefore we can achieve coexistence. Okay. And before I conclude, I would like to talk about an effect called founder effect. Founder effect is a scenario when whether you reach whether a species can exclude the other depends on its initial numbers. If the initial numbers are small, it is going to die off. If the initial numbers are large, it is going to win. So, how do we think about this scenario? So, one way to think about this scenario is consider again the equilibrium 0 K2, which is the equilibrium when only species 2 is present. Okay. Now, let us also consider a scenario that species 1 cannot invade this equilibrium, this population. This means that 0 K2 is now a stable equilibrium. The species 2 has established itself, and if I introduce a little bit of species 1, small numbers of species 1, it cannot invade this equilibrium. Let us also consider the equilibrium in which only species 1 is present. Now, let us introduce a small number of species 2, and we find that species 2 cannot invade this equilibrium. Okay. Now, when both of these conditions are simultaneously present, it is entirely possible. I will leave this as an exercise for the students of this course to work this out. Okay. When both these conditions are simultaneously possible, what this means is that both the equilibrium are stable, and a small number of one of the species cannot displace this already established population of the other species. So, when both these are when both conditions are met, we have the founder effect. Okay. Sometimes it is also known as initial condition dependence. It depends on where you start. If you basically the idea is broadly the idea is that if when you start a species with a large number, it has a higher chance of establishing itself and excluding the other. Okay. But it does not mean that under these conditions only one species will ever survive. It is entirely dependent on the initial or founding population size. Okay. So, now I think we have now covered a good aspect of summary of competition models. So, sort of to summarize what we learnt in the context of competition, there are 4 possible scenarios. Species 1 can competitively exclude species 2, species 2 can competitively exclude species 1, species 1 and species 2 can coexist in a stable equilibrium, and finally the founder effect, where the initial population size determines the outcome of the competition. With the idea that the larger sized population wins. Here chance of winning. So, that is a summary of the Lotka-Volterra competition model. Once again I encourage all the students to sort of work out the conditions for each of them and make biological interpretations of what these mean, and let me again reiterate one subtle point. It is not just the relative importance of interspecies interspecific competition with respect to intraspecific competitions that determines the outcome of competition, but interestingly even the carrying capacity of the populations plays a role, okay. And that is something that is an insightful learning when we analyze the mathematical equations of competing populations. With that note, I conclude our discussion on population modeling, and I hope you have enjoyed, and we will discuss questions that you may have in the live sessions. Thank you very much, looking forward to it.